All right, we are deciding whether we can have notes for the test. Okay, that would be all right with me, but not unlimited notes, like you can look up stuff on the internet.
Yeah.
How about notes on one side of half a sheet of paper?
We're gonna make our
Or
own.
like hand notes.
Yeah, you gotta write your own notes. It's not like you just look up a cheat sheet somewhere.
Would we write it on Notability and then print it out and have it?
Yeah, got it. Yeah, but it's gotta, yeah.
Okay.
Does the size of a paper matter?
Yes. Okay, you guys watching on the video, so typewriter paper, 8.5 by 11, folded in half, one side only. You guys heard that? You guys on the video? So, what, do this for every test?
Yes.
Okay, I'll agree for the first time ever. So we will allow notes on every test, but you have to write it yourself, not like somebody writes it and then prints it out for you. You gotta be your own handwriting. One side of half a sheet of paper. What happens if you have on two sides?
0 straight.
No, then you just can't use it. Then you got no notes. Okay, I'll agree with that. All right, today is the last section of vector calculus. It's on curvature. Now, I'm not sure how these formulas are derived, but they tell you how much a curve curves. The more it curves, the bigger the curvature. So in other words, if a curve is like this, see how it bends a lot? So the curvature is going to be high. Whereas if you have something like that, it bends, but so the curvature will be low. In fact, remember when we watched the TNB frame animation? Remember it also showed the osculating circle? You know what the osculating circle is? Like a tangent circle, kind of, like that. So like over here, at this point, the osculating circle will be bigger. So the relationship between curvature and the radius of the osculating circle is the radius of the osculating circle is the reciprocal of curvature. See, like this curvature is going to be big, right? So you take the reciprocal of it, see how this one is smaller? Whereas this one, the radius is bigger because the curvature is smaller. So when you take the reciprocal, it's bigger. So there are 3 formulas on the notes. See, these are the kinds of things you want to put on your notes, yeah? So you got to figure out which formula is best to use. Well, if they're given parametrically, like 1A and B, then I probably would want to use either the first or the second one. And of course, you guys know what capital T is, right? Remember the T and B frame?
Yes.
That's capital T is the T, the unit tangent vector, but then you got to take the derivative and then the length of it. I forget which ones I used when I made the videos, but if the equation is given as y equals something, like for example number 2, then you probably want to use the third one. Well, what about the third one? Well, number 4, it's given parametrically, but what about number 3? Do you really want to solve for y and then compute the first and the second derivatives? Because notice that the formula, you need the first and the second derivative to compute curvature. Or would it be better to write it parametrically first and then use the parametric ones? For example, okay, let's look at number 3 then. What is the graph of this song?
Oh, that is. Wait, that's in the ellipse.
Yeah, this is an ellipse. Okay, now, what is the parametric? Well, there's an infinite number of parametric representations, but what's a parametric representation for this? Can you just look at it and tell, like, x equals something, y equals something?
2 sine.
Oh, song? You think you got gonna give it?
No.
How do you know? Because look, if you divide by 8, you're gonna get x squared over 8 plus y squared over 2 equal 1. Remember standard form of in the ellipse? So if you square this equation, you will get x squared equal 4 sine squared t. If you square this equation, you will get y squared equal cosine squared t. Divide by 4 here, and then add x squared over 4 plus y squared is equal to 1. Oh, that's pretty close. That's not bad. So what could I have done to like make the coefficients come out?
Root 2
Hmm?
out of like 2 root 2 sine t.
So multiply each one by root 2?
Yeah.
So let's try that then. Is that gonna work? So when you square both sides, okay, just start all over. Divide, so x over 2 root 2 squared equals sine squared t. Y over root 2 squared equal cosine squared t. Add the equations and you get x over 8, x plus y squared over 2 equal 1. There you go. So that would be one way to do it. So you can use these equations. What if you switch the sine and the cosine? Would that work?
Yeah.
Yeah, that would work too. See, so that's why there's an infinite number. And what if I change like the period on the function? Like what if I went sine 3t, cosine 3t? Would that work too? Yeah, so, and how does that affect the particle? Like if I put 3t in 3t, or 5t in 5t.
Faster.
Yeah, that's right, it just goes around faster. And then maybe if you put a negative on one or both of these, maybe it goes the other way. Instead of going counterclockwise, might go clockwise. Yeah, so like I said, there's an infinite number of ways to do it. So once you can write it in parametric form, now remember, this is the same thing as the position vector 2 root 2 sine t, root 2 cosine t. And then once you do that, then I would use either the first or the second formulas. So you gotta figure out which one is the best for you. Okay, so what I want to do today though is I want to look at, can you think of a curve that has a varying curvature? Yeah, let's do a parabola. Okay, I'm going to erase this, is that it? Because we only can use one side of the board when we record. All right, so let's look at the parabola y equal ax squared. So what happens when a is 1? You get your basic parabola, right? But what happens when a gets bigger? Like what happens when a is 2, 3, 4, and so forth? What's going to happen to the parabola? Is it wider or thinner? It gets thinner, right? And if a gets closer to 0, like 1/2, 1/3, 1/4, then it gets wider, right? So when it's like this, the curvature should be big, and then when it gets like that, the curvature should be small, right? Okay, so let's apply the formula. So here, kappa, this is the Greek letter kappa, don't say K. That's like saying Euler. Hey, did I tell you Chen Yi who sent me an email? Remember Chen Yi?
Yeah.
So she's at USC taking, I don't know what course, but her professor said Euler. And then in the class there were snickers. And then he goes, why are you guys laughing? And then they said, oh, it's pronounced Euler. And then the professor said, well, that's the way I learned it, and I'm not going to change, so just get used to it.
What?
If you, come on, Euler, it's Euler, it's not Euler, because he's Swiss.
So he's gonna keep it that way?
Because that's the way he learned it his whole life. He just called it Euler. So, absolute value of f double prime of x all over 1 plus, well, I can't even memorize this formula, so that's why. Squared to the 3/2 power. That's like I said, I really don't know how these formulas are derived. Okay, so, I heard something. So if this is f of x, what would be f prime of that? Why don't we just write f of x? What would be f prime of x? Come on, easy. 2ax, and what would be f double prime of x? 2a. And let's just assume a is positive, so it's opening upward, yeah? Okay, so what would be the curvature? How do you compute curvature? Absolute value of the second derivative, 2a, all over 1 plus the first derivative squared, which is 4a squared x squared to the 3/2 power. Did I do that correctly? Okay, so let's look at the family of parabolas that we have. So when a is 1, you guys know what a basic parabola looks like, right? A is 1. What would happen if a is, say, 2? Then it would be more like this, yeah? And then what if a is like 1/2? Then it would be wider like this, yeah? A is 1/2. So what would be the curvature for each one? What about this one? What's the curvature? If you plug in 1 for a. Park. Oh, we're going to give that the point. Let's say right there, at 0, 0 then. When x is 0. 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 Okay. So when x is 0, what is the curvature if a is 1? What?
2.
Oh yeah, you're right. Okay, Hong, what about when a is 2? What would be the curvature?
4.
Huh? You're right. And then when x is 0 and a is 1/2, what is the curvature? Learner? 1. So the curvature, see how you have a bigger curvature? See, like this one here? It curves more, that's why, right? So the bigger the curvature, the more it curves. The smaller the curvature, the smaller it curves. And then, like I told you, the radius of the osculating circle is the reciprocal of the curvature. So what's the reciprocal of 1? 1. So I don't know what the unit is, but see, the osculating circle would be that. What about when the regular one here? Where's the normal one here? So the radius would be 1/2, so it's going to get even smaller. And then what's the radius here? 1/4, so it's going to be even smaller. So the reciprocal of curvature is the radius of the osculating circle. This is easy. This is just computation, right? So you guys just have to worry about, oh, do I know how to compute derivatives? Can I do integrals? Can I do the binomial theorem? Did you have problems with the binomial theorem last night, Tom?
Yes.
We went over it. Kanashiro?
No.
Did you do it? Then don't, that's it, that's strike 1, no curve. Whatever your average is, that's going to be your average. Don't lie to me in class. Did you do it?
Yeah.
Okay, why did you have problems with the binomial theorem?
Wait, oh, you asked me if I had a problem? No, I just looked at the solution.
We are done. And then look, what of tonight's problem? Okay, look at this. Redeem yourself, Kanashiro. Right here. The position vector, cosine cube t, sine cube t. We talked about this already. What is the graph going to be? No redemption for you. Simao. Hong? Just talked about this one here. Learner.
Alright, I can say. Oh, I don't know myself.
Song? No sense even. Park. That's the hypocycloid of 4 cusps.
I was gonna say.
Come on, x equal cosine cube t, y equal sine cube t. I told you guys this. If you have a, we don't even need this. If you have a circle and you have another circle whose radius is 1/4 of the original one, and you roll it without slipping on the inside of this circle, isn't the graph going to look like this? You get the hypocycloid of 4 cusps. So it says you're going to compute the curvature when t is pi/4, so it's going to be right there. You're going to compute the curvature. See, because anybody can use the formulas, but you guys gotta like know what's going on. Okay, redemption here. Psalm number 4. If I were to graph this, what is the graph gonna be?
That's just like the spring.
Very good. You mean Oh my goodness. Did you really not see that? Well, there you go. Okay, we're gonna play a game and then we're gonna go home early today.